So I think we are good to start. And today it's a pleasure to have our international guest, Rene Meyer from JMU Würzburg, who will tell us on the symmetry-resolved entanglement in AdS and boundary CFTs. So please, Rene.
Thank you, Antoine. Yeah, thanks for the kind invitation to talk here. It's my first time in Binza. It's quite an impressive place. So I'm going to talk about symmetry-resolved entanglement in the context of the AdS-CFT correspondence. And I'm also going to have a second part of the talk about how to calculate boundary conformal field theory corrections to symmetry-resolved entanglement. But let's see whether or not we come there in 1 hour. What is symmetry-resolved entanglement? So I guess everybody knows what entanglement entropy is by now. Symmetry-resolved entanglement becomes relevant when your system, your quantum system, has additional conserved charges. Then you get a super selection structure in your Hilbert space. And symmetry-resolved entanglement is basically the question: what is the amount of entanglement, let's say, in a bipartition in one particular super selection sector? Okay, good. So, but before I get into details, let me say something about the people who actually are behind all this research here. So I'm going to talk about 4 papers here, if time allows. The first 2 here, we started out writing together with, all of them are actually with my former PhD student, Su-Ting Zhao, who is now in Simis as a postdoc, and a postdoc, Christian Norte, who is now in Prague. And then for the second paper, we were joined by Konstantin Weisenberger, who was a master student. He is now a PhD student in Cologne. And for this, and also for the third one here. And for the last paper, we had some help from Giuseppe Di Giulio, who is now in Stockholm, and another master student, Henry Scheppach, who is now a PhD student in our group. So people keep moving up, yes. So just to set the stage, basically, since 2006, when Shinsei Liu and Tadashi Takanagi told us how to calculate the entanglement entropy holographically in AdS-CFT, there is this kind of triangle that emerged, and which basically, where there's basically this relation between semi-classical gravity and strongly interacting quantum field theories via AdS-CFT. And then there is, this ongoing project to calculate, to understand the relation of quantum information theory in the context of gravity via AdS-CFT. And of course, it's also interesting by itself to just look at quantum information measures, the quantum information properties of quantum field theories. So this is this side of this triangle. And so in this talk, I'm going to work on this side. I'm going to show you some results for symmetry-resolved entanglement in 2D relativistic CFTs with Kac-Moody structure, for example. And I'm also going to work on this side, of course, by telling you how to calculate the symmetry-resolved entanglement entropy in this in certain instances of AdS-CFT. Okay, so I guess I don't need to say much about the AdS-CFT correspondence, and also not about that quantum information actually has something to do with space-time geometry. Let me just point out that this whole research program to understand basically the emergence of the bulk spacetime in AdS-CFT from quantum entanglement and boundary theory started with this paper by Van Ramsdonk here in 2010, where he says already in the first sentence here, we argue that the emergence of classically connected spacetimes is intimately related to the quantum entanglement of degrees of freedoms in an unperturbative description of quantum gravity. What he means is the quantum entanglement on the dual CFT. Okay, and so my motivation for studying other quantum information measures like the symmetry-resolved entanglement here. Can we get rid of this bar somewhere down here if it's possible? Sorry. I think we just need to click. Or is it, there's some way of. I think under more. Probably there's something, hide panel, hide this, hide this, yeah, okay, good. Yeah. Oh, so now somehow I cannot change the slides anymore. Sorry. Okay, now it works again. So in German, we have a word for this, which is very hard to translate into English. It's called verschlimmbessern. You want to make something better, but you make it worse, actually. Okay, so my motivation is somehow in this, also in this direction. Like, if we look at more fine-grained measures of quantum information, like in particular symmetry-resolved measures, can we understand something more, get more fine-grained information on the bulk quantum gravity side of the correspondence, okay? Good. So what is quantum entanglement? Quantum entanglement is basically these hidden correlations that you have in otherwise pure states in quantum mechanics and quantum field theory. So for example, if you take this EPR state here, this is made of two qubits, like the qubit of Alice and the qubit of Bob, then you know that this state is basically not, this cannot be factorized here. And furthermore, if you ask Alice to measure her qubit and Bob measures his qubit, and then they come together again and they compare their results, then you find out that there is perfect anti-correlation, and these quantum correlations, these are actually an expression of this quantum entanglement in this state here. Yeah. So, but if I mean, this is easily explained for 2 qubits, but if I give you a state of like 1,000 qubits or so, it's very hard to understand what are the quantum correlations, or equivalently, whether the state can be factorized between these two subsystems here. And so you need some measures of quantum entanglement, and the standard measure to consider for bipartite quantum entanglement, where you cut your system into 2 pieces, is the entanglement entropy. Yeah. So there you go ahead and you start, I start cutting my system into pieces. Usually this is done spatially, but you can also do it in basically in another basis. Yeah, I'm only going to work with spatial bipartitions here. And then there is an assumption that goes in here, namely that the Hilbert space factorizes into a Hilbert space in one subsystem A and the Hilbert space in the other one. This is a little tricky because, we know by now that this works well for ordinary quantum field theories. This also works well for gauge theories if you do something at this cut here. But this, for example, does not work well for gravity. Once you increase gravity there, you need this. It's a bit tricky. Yeah. Yeah. But assuming that you can do this, then you can trace over the B subsystem of, and take your density matrix that corresponds to the state that you're looking at. Typically, we take a pure state, because if you have a mixed state already from the start, you have classical correlations in the mixed state, which are hard to distinguish from quantum correlations, from these quantum correlations here. So you take a pure state with density matrix rho, then you trace over B, and you get some reduced density matrix in the subsystem A, and then the von Neumann entropy is the entanglement entropy. And so if the state originally was kind of independent in A and B, so it factorizes in this in terms of this Hilbert space here, in this Hilbert space here, then this entanglement entropy will be 0, because after tracing out over B, you end up with a pure state in A, and then this vanishes. Okay, so if you do this, however, for example, for the EPR state, which is not factorizable into the 2 subsystems, you end up with such a reduced density matrix for Alice, and then the entanglement entropy is log 2, and also for the other subsystems. By the way, interrupt me with questions. Yeah? For open string theory, well, there are some works on this. The question is, in which space? Do you want to do this on the worldsheet or in target space? In target space, I haven't really looked at these papers. People try to do this, okay? And so all of these definitions in quantum field theory, they involve putting some UV cutoff of some sort. If you can do that, then it's well defined. Mm-hmm. Yeah, but I can show you the papers. Yeah, that's all I can say right now. Okay, yeah, people have attempted this. I forgot there is this. Who's this? There is this one. I forgot his name. There is this one physicist who is originally from Nepal, and he works at CERN, I think. I can find it for you. Okay, I forgot the name. Yeah. Yeah, it's a good question. Yeah, how to do this? It's a bit tricky in general because, as I said, this already is an issue if you include gravity. Right? So the issue is, since you asked, the issue is that so in any have some chalk here, probably somewhere, or here it is the chalk. Okay. So the issue is the following: if you do this for a generic gauge theory, you might first think about a gauge theory, right? Then, okay, let's say we do this on a lattice, some sort, and we say, okay, this here is our entangling region. Then you know that for gauge theory, the proper variables are Wilson lines. And if you have a Wilson line like this here, and you want to say, you have to decide whether this is inside or outside your region A. You have to cut the Wilson line. This means that you're actually adding charges here, like some electron and some positron, for example, for electrodynamics, okay? So this is not such a big issue, because this just means that you're kind of changing, you're basically defining this tensor product decomposition by adding some localized change of your system on this surface, right? But for gravity, this doesn't work naively because a gravitational Wilson line, like if you try to do this in 2+1 dimensions, yeah, then there are no negative masses, right? So there's nothing to add here. Like this is roughly the reason, basically, why you cannot do this Hilbert space factorization easily in gravity. Okay. However, there's this recent discussion about von Neumann algebras, and this gives a different definition of what this minus trace rho log rho here means. And this is the proper way to think about the gravitational setup. So there you basically say, okay, I mean, in full quantum gravity, my von Neumann algebra would be type 1, and then both these density matrices and this trace functional is well defined, basically. So it's a more abstract way of thinking about this without going to this like very concrete definition of introducing a UV cutoff and so on and so on. Okay, that's all I can say about this for now. And in string theory, I don't know. Yeah. Okay, any other question? Okay, good. Yeah, so I'm going to be mostly working in AdS 3 CFT2, just because there as I will review in the next slides, we understand how to calculate entanglement entropy using very powerful methods of 2D CFT. Yeah, so let me just remind you what is the AdS 3 CFT2 correspondence from the bottom-up point of view. So we start out with Einstein-Hilbert gravity in 3 dimensions with negative cosmological constant here, and this cosmological constant, has units of mass squared, so it gives rise to a curvature radius of the ground state of this AdS3 spacetime. This looks like this, and this AdS3 spacetime has some asymptotic boundary, and that's via the usual dictionary of the correspondence is where the dual field theory is defined. In particular, you can do in 3 dimensions, you can do an analysis of the bulk diffeomorphisms, how they act on a boundary state. This is the so-called asymptotic symmetry analysis. And then you find, and this has been done a long time ago, you find that the boundary theory has to have two-dimensional relativistic conformal symmetry. So there's this Virasoro symmetry around here. And so you identify this as the boundary theory as a 2D relativistic conformal field theory with a central charge, which is given by this formula here. And since we are usually working in the semi-classical limit of the correspondence, because otherwise we have to work much harder to make statements about quantum gravity effects here, we take the Newton constant in units of the AdS radius to be small, which means that this correspondence holds for very large central charges. Yeah, so now how to calculate entanglement entropy for a spatial bipartition in AdS 3 CFT2? Well, this was proposed by Rio and Takanagi for general dimensions in 2006. At least they gave a proposal for the leading part of the entanglement entropy in the semi-classical limit, so the leading contribution for small g Newton, for small Newton constant. So what they say, what they told us is what you have to do is basically first of all, you take a time slice in AdS3 here in this situation. That's where your state is defined. And then you have to prescribe, like, what is the subsystem in the dual boundary theory that you want to look at. In order to do this, you have to put a UV cutoff because the time slices, the Poincare disk gets infinitely extended. The distance to the asymptotic boundary is infinite. So you have to kind of regularize this. You basically put a UV cutoff to regularize this. And then you can prescribe your subsystem A here. And this subsystem has two endpoints, U and V. And then Ryotaka and Nagi say, okay, to get the entanglement entropy of A with the outside, you have to calculate the minimal curve that connects U with V that goes through the bulk in this case, because any de Sitter space is negatively curved. And the entanglement entropy is then the length of this geodesic divided by 4 times the Newton constant. Okay. So, and if you use this Brown-Henot relation with the central charge, you find this result here. And then everybody was very happy because this is exactly the universal answer for the entanglement entropy of a single interval in the ground state of a 2D relativistic CFT. Okay, so holographic calculation matches CFT calculation. Okay, so how do we know this CFT result here? This was worked out by these people even before. And so basically what you do is you use the replica trick. So instead of calculating minus trace rho A log rho A, you actually go and you calculate SAN, which is given up there. So log trace rho A to the nth power divided by 1 minus n. And then in the limit n going to 1, you recover this expression. And so it turns out that trace rho A to the nth power or to the qth power here is much easier to calculate than trace rho log rho in a quantum field theory. Okay. So in particular, you can look at this trace rho A to the qth power, represent this as a partition function in the path integral approach. And then you find that what you have to do is you have to take q copies of the original CFT, and each of these copies lives on a single copy of the two-dimensional Euclidean plane here. And the sub-region here, A here, is now becomes a little cut in your plane where basically boundary conditions for the fields are given. This is how you represent the matrix elements of your density matrix here. And then the trace structure, like basically how you sum over these matrices, or how you path integrate over prescribed field configurations here, amounts to basically imposing periodic, some kind of ZQ periodic boundary conditions here. So you say the field configuration here in the upper part of the first of the cut in the first copy is the same as the field configuration in the lower part of the cut of the second copy, and so on. And then you go back to the first one because there's this trace here. Okay, so this is how you basically represent this partition function. So at the end, you calculate the partition function of q copies of your CFT in this complicated manifold, and then you have to normalize by the result for a single copy to the qth power. Okay. Now this is still quite hard to calculate. So it can be done for simple systems like free fermions and for q equals to 1 and 2, for example, where this manifold doesn't have a high genus. But Cardi and Calabrese went a step further, and they realized that this construction, because you have this ZQ symmetry here, and so this construction is basically a ZQ orbifold of the original CFT. And so this and here we are looking at a number which is ZQ invariant, right? So there is no replica symmetry breaking here involved. And so you can basically also just mod out ZQ and go to the so-called twist operator picture, where instead of working on q copies of the plane, you work on a single plane. And across the cut, you have to enforce boundary conditions now that when you cross the cut with some operator from the CFT copy 1, then it becomes an operator on CFT copy 2, and so on and so on. So what's happening is these boundary conditions are enforced by so-called twist operators. These are heavy operators in the 2D CFT that are just there to basically, do this, basically ensure that the boundary conditions are these ZQ periodic boundary conditions here. And they were able, by looking at the Ward identities for these twist operators, they were able to actually characterize them completely, namely as primary operators with a certain dimension. So these are Virasoro primaries with a certain dimension. And furthermore, they were able to show that this ratio of partition functions here is just the 2-point function of these twist operators to the cube power. Okay? And these 2-point functions, they are known in 2D CFTs by symmetry, by conformal symmetry. They are just 1 over distance to the 2 delta, okay? Where delta is the scaling dimension here. So you know everything. You can plug the result together, go take the log, divide by 1 minus q, take the limit q going to 1, and you end up with this result, okay? So the really hard work is already done here in this paper, okay? Good. So this is how you calculate this, and you already see like this is basically, since this is a very simple system, this is just amounts to the 2-point function of this primary operator here. So this is the universal result for any 2D relativistic CFT with a central charge C, okay? And then this matches the holographic result if C is large, okay? Good. So now this finishes my introduction. So let me come to the symmetry-resolved entanglement, and I will first give you the definition. So let's say we start out with a U1 symmetry. Of course, I have to tell you, what is the symmetry that I'm looking at. I start out with a U1 symmetry, and I want to calculate the entanglement entropy in a single U1 charge sector. Then what you can do is you know that you have your charge operator Q in your system, okay? This is just a Noether charge. And because it's a Noether charge, it actually splits into an operator acting in the subsystem that you're looking at and an operator acting just on the complement, okay? And by the superselection structure of your Hilbert space, so basically there is, each state in your Hilbert space has some charge Q total, and then the superselection argument says that the Hilbert space, the total Hilbert space, decomposes into a direct sum of subspaces labeled by these charges. So you pick a state in one of these superselection sectors. This means immediately that the density matrix commutes with Q. And if you now trace over the subsystem B, you can quickly show that the reduced density matrix also commutes with the subregion charge QA, okay? So this means that this reduced density matrix also has a superselection structure, right? So there's basically a block decomposition into blocks, rho A of Q, labeled by the charge Q, which is the charge inside your subsystem A, okay, basically. So, and then the symmetry-resolved Rene and entanglement entropies are nothing but the Rene and entanglement entropies for such a block, okay? So this is the Rene entropy, this is the n going to 1 limit that gives you the entanglement entropy. One has to be a bit careful with the normalization here. These blocks are not necessarily trace normalized, even if this is trace normalized. So you have to normalize by the trace, and the trace is also the probability distribution to measure charge Q and A. Okay, so that's why there are these ratios here. Okay, so this is the definition. And so what does this mean physics-wise? So there is a nice decomposition formula that you can just prove from the definition of the ordinary entanglement entropy, minus trace rho A log rho A, and then like this definition here. So this decomposition formula looks like this. So it tells you that the ordinary entanglement entropy for this subsystem A can be decomposed into a sum over symmetry-resolved entanglement entropies weighted by the probability distribution plus the classical Gibbs entropy of this probability distribution, okay? So what this means is that basically by going to a superselection sector in my subsystem, I've done a projective measurement. I've basically projected down to a particular charge sector, okay? And then what was originally quantum correlations, like measured by this entanglement entropy, now splits into a classical part and remaining quantum correlations. So this is what you do. And if you had more conserved charges, you could do this consecutively more often, yeah? Yeah. So this is basically, what this symmetry resolution does in an operational sense. Okay, good. So if you go through this, for example, for the 2-qubit system here, So let's assume that the Hamiltonian is such that this is easily achieved, that the occupation number in each qubit is like a conserved charge, right? So usually these qubits are some kind of spins, and then the sigma z orientation of these spins are some additional conserved quantity in the system. So this is easily achieved here, and if we now look at the reduced density matrix of Alice's qubit here, that's already nice and block diagonal here. So you see already the superselection structure. And then you calculate the probabilities. These are the traces of these blocks. Then you get a half and a half for Alice to measure qubit state 0 or 1. This is just a 50-50 probability distribution that Alice measures. Okay. On the other hand, if you now normalize these blocks, then this is just the density matrix of some pure state. So there is no symmetry-resolved entanglement in each sector left over. Okay, so this is basically what I just said before. Alice measures the conserved charge, occupation number 0 or 1 in her subsystem. And then in this way, she basically transferred entanglement into classical correlation. Okay, good. Any questions so far? Okay. Good. So now if you want to transfer this into the holographic setup, you first need to fix some setup that has an additional conserved quantity. And probably the simplest thing you can start out with is a U1 Kac-Moody symmetric CFT. So this is a CFT which, in addition to the ordinary energy momentum tensor, also has a conserved current around. This conserved current is a primary operator of dimension 1, so it can be expanded in this way into modes. Energy momentum tensor is expanded in the usual way into modes. And then there is because the current is a primary of dimension 1, it has a non-vanishing OPE, non-trivial OPE with the energy momentum tensor, which means that the correlation functions do not commute here between this sector and this sector, and you get this extended symmetry algebra here. So there's like 3 pieces here. There is the normal Virasoro piece here. Then there is a line that basically says that this is a primary of dimension 1. And then there is an additional piece that tells you that the current modes can also not commute. There is a central extension here labeled by this one number here, the Kac-Moody level K. Oh, you can adjust it to anything, yeah, but not 0. Yeah, yeah. But it depends a little bit. I mean, if you really have a physical system, like a quantum Hall state, for example, then this K is fixed, yeah. So, of course, you can readjust your normalization, but I mean, if you have integer quantum Hall state with filling fraction n, then this is just, filling fraction k, then this is just the level, yeah. Sorry? And this is a good thing. So I assume that this is just independent. But in some situations, like in supersymmetric situations, you have like k is proportional to c or something like this. That happens also. Yeah, yeah. But this is not really important for my arguments later. Yeah. Good. Okay, so we were working in these 2 papers. We were working with this, and yeah. So now what is the holographic dual to such a Kac-Moody symmetric CFT in the bottom-up framework? Again, I'm not talking about supersymmetric situation now. So it's very simple. You basically start with your usual Einstein-Hilbert gravity here. That gives you, in the sense that provides you with this Virasoro sector here. And then in order to describe this conserved current, you're adding a U1 Chern-Simons term, one for the holomorphic part of the current and one for the anti-holomorphic part, yeah? And so they need to have opposite, but otherwise equal Chern-Simons levels so that the parity is preserved, okay? So I add like 2 copies of this Chern-Simons term, one with level k and one with level minus k, and then basically the holographic dictionary has been worked out here in this work a long time ago. Basically, this the gauge field has one component that's dual to the chemical potential and the other one that's dual to the current expectation value. Okay, good. And if you do an asymptotic symmetry analysis also here, you look like how bulk diffeomorphisms and bulk gauge transformations act in this extended system, then you can confirm that the boundary theory has Kac-Moody symmetry. Okay, good. So that's the setup we worked with. And now let me first give you a summary of our results in this first paper here. So we started out by looking at a single interval and the symmetry-resolved entanglement of that setup in this instance of the AdS3 CFT2 correspondence. And so we did two things. First of all, we did a CFT calculation, and we did a holographic. We found a holographic prescription and did an analogous calculation on the holographic side to find matching results for the symmetry-resolved entanglement entropy. And the CFT calculation basically employs an idea by these people in this paper from 2018. They basically said, okay, in order to project down to a particular superselection sector, you have to change your twist operators, because these twist operators, they introduce a Aharonov-Bohm flux for charged operators that move around these endpoints. And then this implements a projector from this Hilbert space to one subsector. I will explain the details in the next slides. Okay, so you have to kind of give these twist operators a charge in the one case. This charge is related to, in a sense, the subregion chemical potential mu here. Okay, and on the AdS side, we've quickly figured out that to calculate this to induce this Aharonov-Bohm flux here, what you really have to do is you have to add an object that basically generates a magnetic field around it. So this is a Wilson line that's charged under this bulk Chern-Simons gauge field, right? This Wilson line is like a infinitely thin current distribution, and so an infinitely thin current distribution, and induces a magnetic field around it. And if you take a charged operator now and move it around, you will pick up a phase as well. So, and this Wilson line is supposed to follow the RT geodesic in order to not break replica symmetry. So this is the AdS side this is the AdS prescription for the symmetry-resolved entanglement that we came up with. So if you do this CFT calculation and you do the AdS calculation, then you find matching results. So we are very happy about this. So this is the result for the entanglement entropy for a single interval with charge Q in this interval. There is like a leading piece here, which is just this Cardi-Calabrese piece that I talked about before, C over 3 with this factor 2 here, log distance length of this interval over epsilon, okay? And then there is a subleading piece, which is new, which goes like log Chern-Simons level or Kac-Moody level over 2 pi times over pi times log distance over epsilon. So this is log suppressed. This is smaller than this in the expansion, in the usual UV cutoff expansion that takes the length of the interval over the UV cutoff large, right, or the UV cutoff small. Another important point here is that this result shows equipartition of entanglement. This was already found for a free boson here in this paper here. So equipartition of entanglement means that the result actually doesn't depend on the amount of charge in your subsystem at all. So this only depends on the Kac-Moody level K. Okay, and this is quite remarkable and can be traced back purely to the structure of the Kac-Moody algebra. I will explain in 1-2 slides how this works. Okay, so the fact that the symmetry-resolved entanglement entropy is independent on the amount of charge in your subsystem is directly related to the simplicity of the Kac-Moody algebra structure. Okay, good. Yeah. Okay. Then in this next paper here, we did a couple of further checks here. I will just tell you what we did, and that actually the result matches again on the AdS and the CFT side. So we looked not just at a single interval in the ground state, we also looked at a single interval in excited states. There's like a very convenient way to get excited states in AdS3 CFT2. Namely, you can add either uncharged or charged heavy primary operators, one at the asymptotic past, basically, of the 2D CFT and one at the asymptotic future. And if you do this with an uncharged heavy primary, heavy means here that the scaling dimension scales like the central charge, then the bulk geometry gets excited in such a way that you actually insert a conical singularity here in the center of AdS. So you somehow this insertion of this very heavy operator cuts out a piece of this disk here, of these Poincare disks. You glue it together again, you get a deficit angle, so you get a localized curvature singularity, which is of a kind of a Meyer type. And if the operators are charged, then you also have to run another Wilson line in this Einstein-Hilbert-Chern-Simons setup that I showed you. You have to run another Wilson line along this conical singularity to induce the charge at infinity. So also here, we did a CFT calculation and the AdS calculation with our Wilson line prescription. The CFT calculation involves now a 4-point function of heavy operators, two such insertions, plus 2 twist operators. You can solve this with well-known large C techniques, and the AdS calculation involves, calculating the effect of these 2 Wilson lines here. Both results match again. Okay. We also looked at 2 intervals in the ground state. There you already know for the usual entanglement entropy that there is a transition happening in the large C setup. Basically, if the intervals are far away from each other compared to their distance here, then the RT geodesic connects the 2 endpoints of each interval. And if they come closer, there is a connected configuration where you connect these 2 endpoints and these 2 endpoints. And on the CFT side, this means that this 4-point function of twist operators is for the disconnected configuration is dominated by the S channel in the OPE picture, and if you come closer, then it's dominated in the T channel. Yeah, and there's some kind of transition happening here. So also here we find exactly the same structure for the symmetry-resolved entanglement entropy. So the Wilson lines basically undergo the same transition. Okay, good. So how do we do this? So let me first talk about why we need to introduce this basically this charge for the Kac-Moody twist operators. So the important point is that we went through the charged moments. So what you really want to do is you want to define a projector onto a subregion charge Q sector, okay, to pick out this one particular block in the reduced density matrix. And this projector can be represented in terms of a Fourier transformation, assuming that the spectrum is continuous, or otherwise you have to take some generalized Fourier transformation. For U1, this is what you should do here. And then basically inserting this projector into the partition function, into the Rene partition function, amounts to inserting this operator e to the I mu subregion charge. Okay, so this is the important thing, and this whole partition function, which now depends on the subregion chemical potential, is called a charged moment. Okay, so this e to the I mu qa. This e to the I mu qa is basically a non-local operator that runs along your interval A here, right? So there's U, there's V, and this qa is the local integral over the charge density, like this. Okay, so this is a non-local thing, and you might think it's kind of hard to deal with it. But the important point is now you can do a little calculation that kind of factorizes this into a piece that is localized at the one endpoint and a piece that's localized on the other endpoint. Something like this. And these are local vertex operators now. We characterize them. They are primary operators again with a particular charge, U1 charge, and a particular scaling dimension. Okay, and this is the main calculation that you have to do here. So you basically get an additional contribution from these localized operators in the replica setup that shifts the scaling dimension a little bit. And now, since these vertex operators are sitting exactly at the same place as the Kac-Moody vertex operators, you can also understand this as an additional charge added to the original vertex operator, and then you get a shift of the scaling dimension. And if you remember, the original calculation by Kac-Moody was only depending on the how the scaling dimension depends on the replica index n, and so there's going to be a little change here now. Okay, good. So this is what we basically did in this first paper. Why does this work out? Well, I mean, this is basically a path-ordered exponential for U1. It's a trivially path-ordered exponential running along this interval. And if you remember how you treat this in QFT with the time ordering, for example, then you can rewrite this as a sum over n, 1 over n factorial, and then what do you get? I mu to the power n, and then you have nested integrals here of these currents. Okay, and this thing you can rewrite by restricting the integration range into consecutive commutators of these currents, but the commutators of these currents are given by the Kac-Moody algebra. And this is why this result only depends on the structure of the Kac-Moody algebra at the end. Okay, so yeah. Okay, so at the end, you do this, you get this charged moment. You do the Fourier transformation back to the charge projected partition function. You take the n going to one limit, you get the symmetry-resolved entanglement entropy, and this is the result. Okay, good. So yeah, so this is the CFT calculation. How much time do I have actually? Oh, 15 minutes plus x, or just 15 minutes? A little more maybe. Okay, we'll see. Okay, good. So what do you do on the AdS side now? On the AdS side, you have to construct the replica manifold first. It turns out the replica manifold here is really simple. After a uniformization transition, a uniformization map that brings this to a nice spherical shape. What you get is basically this is not really written in this shown in this picture. You get this kind of field orange structure here, where you get n copies of your original interval A here, and then the Wilson line that we add in the bulk runs right through the middle of this peeled orange. And so what the calculation that we did to get the symmetry-resolved entanglement entropy here is described in this slide here. So what you have to calculate to get the symmetry-resolved to get this charged moment and hence the symmetry-resolved entanglement entropy is you first have to calculate the subregion charge density induced in the replicated setup at finite chemical potential mu. And once you have this, you automatically have the logarithm of the ratio of partition functions for these charged moments Zn of mu divided by Zn of 0 by this first order differential equation. Once you have this, you can integrate once with respect to the chemical potential with some obvious boundary condition. So you get the charged moment partition function, and then you Fourier transform back to the charge projected partition function and so on. Okay, so this is what you have to calculate, and this you can calculate by basically putting this Wilson line in the replicated setup and calculating the flux that's induced by this Wilson line via the Chern-Simons equations. So this is the Chern-Simons gauge field strength, and this is basically the current distribution that is induced by this Wilson line, the source that's induced by the Wilson line in the bulk. So this is what you do, and you get the same result. Yeah, good. Any questions so far? Okay. So this computation is done in 3 dimensions. Yeah. Well, I will say something about. I can say something about higher dimensions. There is a generalized setup by Pablo Bueno et al. Where they say, okay, so you see the problem is what do you want to do in higher dimensions? In higher dimensions, you don't have this, the twist operator picture, right? This is a big problem. What you have is let's say in AdS4, the space is R2. Then you have like some curve that separates inside from outside in the simplest case. And now RT tells you, okay, you have to calculate the minimal surface here and calculate its area. And what Bueno et al. Did is they basically went ahead and they generalized our setup by saying, okay, now I take a So if this is AdS d plus 1, I take a d minus 1 form field that I pull back and I couple the RT geodesic to that, okay? And then I do the same thing. I calculate the flux induced by this thing in some Maxwell setup for the field strength for this field. Interestingly, they get some proper result which matches CFT arguments, okay? It's different from the paper we looked at after lunch, where they do some other trick. So the higher dimensional case is not completely settled. That's what I would say. I don't understand what's going on between these two cases. Yeah. So they work with these p-form fields, and so basically in higher dimensions you can also get some universal results for the symmetry-resolved entanglement entropy for a simple region like a sphere or a strip. They reproduce this. But the paper we looked at also reproduces something like this, but I don't know how they fit together. So there must be some way. Yeah. Mm-hmm. Here the F is the Chern-Simons field strength. Mm-hmm. Yeah, we are looking at this right now. And there was a paper today that does something similar already. Yeah. Mm-hmm. Yeah. Mm-hmm.
I'm not quite sure what that because the symmetry will count on the strata, they should be preserved, right? Otherwise, when n goes to one back, it should be.
You definitely don't want replica symmetry breaking. That's all I can say now. But monopoles you only have if you have additional matter in your system. Okay. I cannot say anything really clever, except that one has to really analyze the situation, right? So the point is, I'm doing Einstein-Hilbert here, Einstein-Hilbert-Chern-Simons here. We have looked at Maxwell already, not published yet, and Maxwell-Chern-Simons, but we have not started adding matter yet, charged matter, because that makes the whole situation a little more complicated, right? So, but I'm sure it can be done. One could try to do some. Let's discuss this later. I think it's a longer discussion. Yeah. Any other questions? Okay, good. So yeah, so at least so in these situations we find agreement between the CFT and the AdS side of of the correspondence. Okay, so now let me just say one thing about higher spin, since Shailesh is here and he's an expert in higher spin, for example. So this is this third paper here. So originally we wanted to start out with higher spin, but we were no experts in higher spin, so we first looked at this simpler setup. But if you look at higher spin, so you have this let's say you have a W3 symmetric CFT where you have an energy momentum tensor and a spin 3 current instead of the usual spin 1 conserved current. Then you know that there is this holographic duality to SL3R higher spin gravity in 3 dimensions. And so you can ask what happens there in terms of symmetry resolution. Now, it turns out to be a bit more tricky because in that case, we were not able yet to completely work out the Wilson line picture. But what you can do is you can use this trick that was developed by Cassini, Huerta, and I think Myers long time ago, where you say, okay, this partition function here, in this case, trace e to the I mu qa rho a to the nth power. I can map this to a grand canonical partition function for the CFT, but not on flat space anymore, but basically on the hyperbolic upper half plane. And this you can calculate using purely thermodynamic arguments. And in the gravity side, you can also calculate this by just looking at the grand canonical partition function of a so-called topological black hole. This is a black hole with negatively curved horizon, and chemical potential is fixed. And these results were known for a long time, so we can just use them. We also found a new way to calculate this actually, but the main point is here is like we can just use this result. This is given as an expansion in terms of chemical potential to 6 or 8 power, it is known. And if you take this and you Fourier transform back, then you take the replica limit, you find that for higher spin CFTs, there's clearly a breakdown of equipartition for the symmetry-resolved entanglement entropy in the large C limit. So what we find is that the symmetry-resolved entanglement entropy, roughly speaking, becomes C over 3 times some function of the subregion charge times log L over epsilon plus subleading terms, okay? So there is something really violent happening here. This higher spin, the higher spin algebra, which is much more complicated, is nonlinear, for example, does something very different from U1 Kac-Moody. This is also to be contrasted to the West-Zumino-Witten case. In the West-Zumino-Witten case, you find the ordinary Cardi-Calabrese term to leading order. Then you find this log-log term. Distance over epsilon. And then you find a constant term which goes like log dimension of the representation of your non-abelian Kac-Moody algebra. And so here the breakdown of equipartition of entanglement is actually sub-leading, but here it's leading in the large C limit. And I don't claim that I understand why this is so violent, but that's all, okay? So so I think there's probably a lot more things that can be understood in the higher spin case. So are there any questions? There is, let me say, in the way how you usually build this up here, if you're not looking at this HS lambda type duality, but you're looking just at SL3R, then this is a CFT which has a clear finite number of low-lying operators, and then you don't know what happens higher up. HS lambda is this equally spaced case. Yeah, we didn't look at this. These instances have other issues, like, for example, I think there is like issues with unitarity here and so on, which are only solved in this HS lambda case, but definitely this calculation can be done. Okay, yeah. Sorry, this has a what? That I don't know. I'm not an expert on non-invertible symmetries yet, so it has to. Yeah. So there is an energy momentum tensor of usually Virasoro type, and a higher spin current. This is this, and this is the OPE that just tells you that this is spin 3 and also scaling dimension 3, right? And then there is a WW OPE, which is a bit more complicated. I don't have it here. I could show it in the paper to you later. Yeah. 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 Okay. If there are no more questions, so let me come. I mean, maybe let me just come very briefly to the second part of my talk. So this is about this, BCFT corrections to symmetry-resolved entanglement. But I will just give you a summary of the whole story in view of time. So basically, what's happening is, so why do we want to consider boundary conformal field theory? Well, it turns out that these results that I just showed you here, they are actually only the leading couple of terms in the UV cutoff expansion, and the subleading terms they depend very strongly on actually what kind of boundary conditions you use when you cut your system into 2 pieces. Okay, and this is related to how you actually define this Hilbert space. tensor product decomposition here, you cannot really do this naively, right? Because in quantum field theory, your quantum fields are operator value distributions. They are smeared against some test functions. And if you just do some hard cut somewhere, then these test functions, they will not respect this cut. They will have some like exponential fall-offs of some type. And so it doesn't make sense just to make a hard cut. What you really need to do is you need to define what is your Hilbert space with the cut. Like you have to put boundary conditions. And also the other part, and then you're in business again. And this is what BCFT is all about, okay? So how do you really do this? Well, you impose some boundary conditions. You say, okay, I take my single interval, let's say, in my 2D CFT, and I make this, this entanglement interval a little thick, and I glue in some little circles here. And on these circles in particular, I put some boundary conditions that are compatible with conformal symmetry, okay? So the standard choice is just conformal boundary conditions here, t equals to t bar, like in the open string case, because in this way you preserve at least half of the original Virasoro symmetry, okay? And for the conserved current, in the U1 case, you have a choice. You can either choose plus or minus, let's say, on each endpoint. And the plus sign corresponds, I think, to Dirichlet and the minus to Neumann boundary conditions. As I remembered correctly, okay? So, so this is like in the usual open string case. And then with this choice of boundary conditions, you can directly write down a local set of conserved charges. Local means just defined in the subregion here. So this is just the ordinary modular Hamiltonian, and this is the subregion charge now. And this is the appropriate other combination of these two currents here. Okay, and the Hilbert space then basically furbishes a representation of this so-called chiral algebra. So you're basically defining the subsystem Hilbert space with boundary conditions alpha, beta. Here, this could be Neumann, Dirichlet, Neumann, and so on. You're defining this by the representation theory of this local algebra. This is what BCFT is all about. And this was worked out by these people some time ago. And so now what we did in this paper is we looked at the free boson. The free boson, I don't think I need to explain here. There are like two conserved currents, right? So this is just like the open string. There's this one, and then there's a topologically conserved current. And if you go to complex coordinates, you end up with one holomorphic and one anti-holomorphic current. And, this again, the plus sign here is the Dirichlet boundary condition. The minus sign is the Neumann boundary condition. Now, if you want to do symmetry resolution, you have to actually make sure that there is one combination of these currents that's still preserved. Yeah. So this somehow breaks like the two copies of Kac-Moody down to a single one. But if you choose like, let's say Neumann here and Dirichlet here, then the two conserved currents on each side are different. So in total, there's no conserved current. So you better choose Neumann, or Dirichlet. And in these cases, you can also deal with, but I will not say anything about this. And then what you have to do to basically just write down, the Rene partition function for this system here, which is now purely defined on subsystem A, is you replicate this geometry n times in the usual way. Then the trace over B is already taken care of because we defined the system purely in terms of the subsystem A, right? The rest is already kind of traced out. And then you map this via a uniformization map to an annulus with some length related to the length of the subsystem divided by the UV cutoff again. The UV cutoff is kind of the radius of these little disks. And the circumference is 2 pi times the replica index. And this you can usually deal with, right? There you can write down a partition function on the cylinder with these boundary conditions and calculate it, okay? So this is basically what is proposed in these two papers here. So in particular, the reduced density matrix is now just, what is this modular parameter to L0 to the power L0 minus C over 24 divided by the trace. So the partition function itself that you're looking at is just this trace over this so defined Hilbert space, open string Hilbert space in a sense, of Q to the L0 minus C over 24. Okay, good. And now what is the relation with the symmetry resolution? So let's say we choose boundary conditions that we still have some symmetry left over. Then we can go ahead and we can just take this in general, we can take this partition function here and we can expand this into characters of the representations of this chiral algebra that I just talked before. There's also some there are some multiplicities showing up here. And now if you do this in the presence of an extended symmetry algebra, then you will just expand into characters with respect to a particular representation. And if you're lucky, like for the free boson, you also know these characters and you know the multiplicities showing up, so you can completely do this expansion, and then you pick out one sum in this expansion here. This sum goes over subregion charges Q, and this directly gives you the charge protected partition function. So you don't need to go through all this charged moment thing. Yeah. And this is what we did with for the free boson here. Yeah, the characters are known. They're in every good CFT textbook. They depend on the subregion charge Q like this. There's the dedicated eta function showing up. So you see this is the character of a Virasoro primary representation with charge Q, and then you go down with the Verma module with your Virasoro creation operators. Okay, good. And yeah, so then the charge protected partition function is given to you for free. So you can just read it off. And now here comes the interesting result. So if we now take the we look at the charge projected Rene entropy. This is 1/1 minus n log ratio of this original, Rene partition function over the nth power of the single copy one. Then you find that the charge dependent part here completely drops out for the free boson. Yeah, so this is just because the characters have such a simple form. So here we find that to all orders in the UV cutoff expansion, this charge projected Rene partition functions, and hence the symmetry-resolved entanglement entropy also, this is the symmetry-resolved Rene entropy, the symmetry-resolved entanglement entropy also is completely independent of the subregion charge, right? So this is the expansion in log distance over UV cutoff here. There are the known terms, like this is the Cardi-Calabrese term before taking the n going to one limit. This is this log term. There's this constant term that I talked about for single boson. The Kac-Moody level is 1, right? So this is what you get here. And then there are a whole bunch of terms which are exponentially suppressed in log distance over epsilon. But all of them are really charge independent. Okay. So yeah, and so this is of course the case because we've chosen very particular boundary conditions, like these boundary conditions here, which basically preserve half of the previous 2 copies of the Kac-Moody algebra. Okay, good. So that's all I want to say about the second paper. This is our main result. You can do this. You can basically directly read off the charge projected partition functions, and then you get, we find this equipartition to all orders in the UV cutoff. So let me conclude. View of time. So I hope I could interest you to look at symmetry-resolved entanglement in the holographic setup. And for me, this is basically, some way of getting new tests of this AdS3 CFT2 correspondence. We looked at the Chern-Simons case. Now we're also looking at the Maxwell Chern-Simons case. We find all this breakdown of equipartition at large C in the higher spin case. And the BCFT approach is very powerful, yields exact results due to the remaining symmetries. And we could show that this equipartition actually holds to all orders for free boson. There's a lot of stuff that you can go on doing here. You can symmetry resolve other instances of AdS CFT, as you just said. I mentioned Maxwell Chern-Simons plus matter. Maybe look at some top-down systems, these kind of things. You could look at other quantum information measures, what they do in each, super selection sector. There's this paper that has a proposal for higher dimensions. Today there was another work by Zhou Yang and his master student Yuanzhu Huang from Fudan University, where they have another way of basically treating the higher dimensional case. They are basically using this Cassini-Huerta-Myers trick. And again, I don't understand what's the relation between this and their approach and what we are looking at now. You could look at non-abelian symmetry groups. There are some work and some results by Oguri et al. Here from 2 years ago. Good question is what are the implications on bulk entanglement, right? How do quantum corrections play with the symmetry resolved entanglement. What about non-invertible symmetries? There are some works right already here, which I didn't cite. And of course, there may be a lot of field theory and condensed matter applications of symmetry-resolved entanglement in different setups. Yeah, there's something in this paper by Christian from 23 where he basically looked at symmetry resolution with respect to a single Werner module, and he relates the symmetry-resolved entanglement entropy to the quantum dimensions of operators showing up in the CFT. Yeah? So there's already some starting point here. So I think there's a lot of things that can be done. Yeah, and yeah, thanks for your attention.
Yeah, awesome. Any questions to Rene?
Logically massive term, the gamma wedge count. Right. So
this is, I have a U1 Chern-Simons field, right?
yes,
But gamma, yeah, so adding higher derivative terms is also something one could look at. But then you have to ask, what does it mean to symmetry resolve here? Like, you know, with respect to which super selection sector you're really working, right? Yeah.
just one quick question about the formula that you showed with the sum over logs.
Mm-hmm. You mean this one here?
Yes, this one.
Yeah.
Does it have? So I remember Gopakumar and Gabriel Saha's computation. They had they could arrange this into a product form because sum of log, so, and that ultimately kind of works itself into a McMahon function.
Like what says
into
what?
a McMahon function.
Okay. Yeah.
So it has interesting like combinatorial properties, partition properties. Have you considered maybe?
I haven't thought about this. We can discuss this later. Yeah.
Kac-Moody, Gabriel, which algebra did they consider? I think in their case it was always has been lambda algebra.
Yeah.
It actually. So you have to look at the multi-particle partition.
I mean, here this is not a
SL2,
holographic
SL3
result. Yeah. This is not a holographic result. This is for a single free boson. Okay. Yeah, but I mean, of course, I mean there may be some rewriting of that type also, which might have to do with the fact that there is some structure here, like as you say, some multi-particle structure. Yeah.
So Rene, maybe a related point for me. When you do your partition function, so you compute those characters. So these are characters purely of this chiral algebra that is arising in
Yes.
case, so there is something on top.
Yeah, so these are the characters of this remaining U1 algebra.
And just that, okay.
Yeah.
And how much can you consider this mixed boundary conditions and DDM?
So the mixed boundary conditions are actually, yeah, you can.
Z2 is
Exactly. So the point is there's some remaining Z2 symmetry. We also looked at this, and then you get some, basically the two charge projected partition functions are not equal, but okay, I mean, why should they be, right? But the interesting thing is if you have ND and DN boundary conditions, you actually break both conservation laws.
Yes.
But there's a twisted U1 that's left over. So you basically, you know, you can make it directly into a Neumann boundary condition by adding a phase of pi. Yeah. So if you could symmetry resolve respect to this twisted U1, we haven't done it. Yeah. I mean, surely there will be some interesting outcomes.
Twisted always can bring you up to the
Yeah.
Okay.
Yeah.
Good. Any other questions? While people think, I just check Zoom.
It's a bit tricky as you have to do all this like brains cutting off the space thing and so on. So yeah. If you do DN and ND, well, we can talk about it. I mean, yeah.
Let's thank Rene.